Welcome everybody in the audience and to our distinguished members of the panel. Thank you for coming out today to hear our proposal for the Gemini Mars design competition. We are Team Itinerary of Purdue University. Defined in Latin, itinerary means a journey or a march. We feel that, like the Apollo 8 missions, this mission serves as the stepping stone towards eventually landing on and colonizing the red planet. Our goal, as posed by the Mars Society, was to design a two-person manned flyby mission to Mars that is launched no later than 2024, as cheaply, safely, and simply as possible. Departing Earth September 6, 2023, we embark on a 500-day mission to Mars. You might be wondering why we have Venus in this trajectory. That is because at the Itinerary Space Store, we are offering a 2-for-1 deal on this mission of a Venus and a Mars flyby. So on February 15th, 2024, 162 days into the mission, we fly by Venus. From Venus, we go to Mars, June 20th, 2024. And from Mars, we round and start heading for home to complete the interplanetary home run, landing safely on Earth, January 18th, 2025, 500 days into the mission. Next, I will be talking a little bit about our assembly and departure operations. We will be utilizing 2 launch vehicles, the Falcon Heavy and the SLS Block 1B. You will notice on day 1 and day 0 and day 1, the configuration, we are holding on to the Falcon Heavy upper stage as well as the enhanced upper stage from the SLS Block 1B. On day 2, we assemble our stack in low Earth orbit, 300 by 300 kilometers. And on this day, we will also execute a Falcon Heavy, a boost burn using the Falcon Heavy to push us up into a 300 by 3,500 kilometer orbit. On day 3, we jettison the Falcon Heavy upper stage. And on day 4, we ignite the EUS to put us on an Earth escape orbit with a V-infinity of 5.2 kilometers per second. Up next to talk a little bit more about our launch vehicles is Rob Potter.
Hi. So to go into a little more detail of why we are doing that setup is we tried to put margin everywhere. And so our system consists of the Falcon Heavy launching the super extended Cygnus, which has actually been proposed by Orbital as a deep space version of their module. And then on the right, we have the SLS launching the Orion capsule with the European service module. And so what that gives us is the Falcon Heavy has some fuel left in its second stage, and the enhanced upper stage on the SLS has a lot of fuel left. And that was calculated using an optimal launch trajectory that we created. And so the reason we're having to hold on to that Falcon Heavy second stage is we'd have to be 10 metric tons lighter in order to not have to use that extra propellant. The other option is we could do an elliptical rendezvous. However, NASA, being risk averse, knows LEO, and so we felt at this time the trade won out to just stay in LEO and hold on to that second stage. And so what this means, though, is that we have 2 issues. Is that boil off, we need to hold on to those second stages for up to 3 days. So we're going to have to add some MLI layers to reduce the boil off to 1% per day. And then the other issue is that most of these second stages are only built to handle up to 8 hours in orbit. And so they need to survive for 3 days, whether that's increased battery mass or being tied into the power system on board the 2 payloads. And then next slide. So here's a mass breakdown of when they're actually connected. You can see that with like Orion and Orion service module, we have a 10% mass growth. And that's because they're pretty well-defined systems. They're pretty far along in their development. So we don't expect too much mass growth. However, on the other systems that aren't well-developed, we have a 30% margin on there, which is a pretty standard industry margin. And so what this adds up to is our total is about 50 metric tons that we have to push. A lot of that mass is actually the enhanced upper stage, which does that second boost burn, weighs about 14 metric tons. And we'll get into how that actually helps us later on. So if you want to go on. So here's our power and thermal system. Starting with the power, we do have 6-meter diameter ultraflex solar arrays, which are upgraded from the Cygnus 3-meter diameter. And in addition to that, we have the European service module generates up to 11 kilowatts at Earth's distance. So as we fly closer to the sun, we're going to generate more power, and we start angling those solar arrays so that they don't get too hot, and we produce a constant power of around 20 kilowatts. And then when we start going away and get out past Mars distance, we still generate up to 8 kilowatts of power, and that allows us about 150% of what power we need in case of emergency. So just if we get hit by a micrometeorite or something that takes out one of our solar arrays, we're still good because we only need 5 kilowatts and we're generating 8 in the worst case distance. And then thermally, you can see these the spike here in this red line. That's if we weren't holding on to the EUS. And so we are holding on to the EUS, which provides a thermal shield while we go to closest approach towards the sun. And that actually cuts it down to about 13 kilowatts, which is about the same heat load or heat rate that the service module would experience at Earth's distance if it was just directly facing the sun. So hopefully not too many modifications would be needed in order to reject the heat that would still be getting through the EUS. And then in addition, that provides a pretty stable environment for the rest of the spacecraft, which will be hiding in the shadow of the EUS during that closest approach. And then we also did radiation analysis. We are leaving during solar max, so that reduces the GCR levels, but increases the solar radiation and also increases the likelihood of getting hit by a solar flare, which again, the EUS saves us there. With between it and the European service module, we get about 80 grams per centimeter squared in the solar direction, which reduces the dose from a solar flare down to about 50 millisieverts. The rest of the GCRs from the 500-day trajectory add up to about 350 in the worst case. And so what that means is our total dose is around half of what NASA's limits are, for including the 95% confidence interval. Their limits are 820 millisieverts for a 50-year-old female and about 1 sievert for a male astronaut. And so we are well within NASA's standards. And go on. And so now that we've gone through the closest approach, we're flying out towards Venus, and we're going to get a nice close flyby around 5,000 kilometer altitude. And so how are we doing on supplies? Well, Glenn will let us know how he's keeping the crew happy, healthy, and hydrated.
Our life support system is designed to maintain the optimal levels of water, oxygen, humidity, and all other environmental components of the cabin. For our water recycling system, we use the Paragon IWP system, which recycles 98% of all non-brine substances, as well as removing 99% of all contaminants from the recycled water. The system is well known for its reliability, only having one moving component in the entire thing. And what's notable, too, is the initial reduction in water mass required for this system. We use about 1,300 kilos of water. Using a Sabatier method, you would need about 2,000 kilos more. A purely consumable method, you need about 4,000 more. Humidity in the cabin will be controlled through the condensing heat exchange, which will recycle the water further, or using the carbon dioxide removal assembly, which will run it over its desiccant beds to remove it from the atmosphere. Atmospheric losses in the cabin will be supplemented by oxygen-nitrogen tanks, which will maintain the 1 atm pressure inside the cabin, as well as maintain the optimal balance between the atmospheric gases. During this mission, the crew will experience several psychological stressors: isolation, interpersonal conflicts, perceived lack of outside help for mission support. Maintain safety for the crew and mission success. We must mitigate these to have minimal effect on the crew and its mission. For mood disorders such as major depressive disorder, which is well documented in Earth analog experiments, with about 40% of participants having symptoms. We're using cognitive behavioral therapy, which is equivalent to a pharmacological approach without the need to sedate the crew using medications. For isolation, this is the first crew to ever leave the site of the view of Earth. So isolation will be a major concern during the mission. We will use a combination of leisure time and mission diaries, as Matt Damon has shown here expertly. The health of the crew is of the highest priority. It's solely the reason why we're going with this. Maintaining bone mineral density and minimizing the loss to muscle mass, as well as preventing medical emergencies during flight, is the only way to ensure the success of the mission. On average, 1.5% of your bone mineral density is lost per month in a low G environment. So to counteract that, we use a regimen of biphosphonates, which have the dual effect of reinforcing bone integrity by slowing the reabsorption of bone minerals into the bloodstream, as well as lowering the risk for hypercalcemia and other medical emergencies due to that. For muscle mass loss, we use a combination of the iRed and treadmill, which has a proven efficacy on the ISS, using very minimal muscle mass loss. For payload science, we focus heavily on international collaboration and enabling technologies for future long-term duration missions. Most notably is the aqueous immersion surgical system, which allows for low G surgery on like synthetic cadavers for this mission. We also use 3D printing, which would allow for small machine components to be created just to test its feasibility in space. On June 20th, we finally arrive at Mars. The crew will get an excellent view of the red planet from 1,400 kilometers up. And here is Diego Martinez to talk about how we'll get back.
Thank you, Glenn. All right. So for our communications platform, our crew will be taking a lot of HD videos, a lot of pictures, and they'll be wanting to share that information with the people on Earth. So this platform that we decided to use is a laser communication system with a 1-meter backup dish. And we've selected this laser communications for several reasons. Most notably are its benefits in both transmit power and data rates that you can see behind me. The benefits in data rate really come in handy. As you can see, we have 5 megabits per second when we're at Mars versus a 1-meter dish, which would only be able to provide about 0.5 megabits per second. Now, the technology has been proven with the lunar laser communications demonstration that has already flown, and will have further flight heritage with the laser communications relay demonstration that will launch in 2019. Fast forwarding about 200 days later, we are now arriving at Earth, and we have to consider our entry, descent, and landing. On the upper left-hand plot, you can see our altitude versus velocity, and you will notice 2 spikes. For that reason, we are including a skip entry as opposed to direct entry. And we've done this also for a number of reasons. Most notably are its benefits when it comes to G loading, as you can see in the upper right-hand corner. Now, our crew will be sustaining 4.5 Gs at 90 seconds. However, that G load is segmented into 2 different sections, which are much more manageable. When we look at the thermal loading for Orion, the baseline heat shield for Orion would not be able to handle the amount of thermal loading that Orion would face. And for that reason, we have decided to use a heat shield developed by NASA Ames Research Center called HEET, or as our team likes to call it, HEAT. Now, the capabilities of HEAT are double of what will actually be experienced during the voyage, so thermal loading is something that we are not too concerned about. And with that, we have finally arrived at Earth, January 18th, 2025, and we can now address one of the main concerns of the opponents of a Mars flyby: cost. So as you see behind me is our cost breakdown. We utilize NASA's work breakdown structure. In NASA's life cycle managing, we would be considered in pre-phase A or conceptual studies. And the type of cost methods that best used in this conceptual studies are analogies and rough order of magnitude, which was utilized for the majority of the different sections you see here, with the exception of our spacecraft. Since it is a custom-built spacecraft, we decided to use Johnson Space Center's Advanced Mission Cost Model, which has been used in previous missions, and that spacecraft accounts for about 58% of the total cost, bringing our total to $6.79 billion. And that includes the 30% NASA reserves that NASA does like to have. However, that $6.8 billion is being spread out over 7 years, and that's really where we get to start really start to see the benefits of launching in 2023 as opposed to 2021. If you look here, you can see that the costs will never exceed more than 10% of the NASA budget for that specific fiscal year. And if we look at the total NASA budget from 2017 to 2023, we never exceed 5% of the total NASA budget, which definitely increases the mission feasibility of our design. So, to wrap things up, we have been posed a mission to design a two-person crewed system to fly by Mars as cheaply, safely, and simply as possible. Now, our system does this in a number of ways. A, we have a very short time of flight. I think this has been the shortest time of flight of any of the designs you've seen so far today, 500 days. That reduces risk in every sector of design. All our hardware that we are using or utilizing is either in the late stages of development or is already developed, which increases both safety and simplicity. We are including the industry 30% mass margin standard, which again increases the safety of our mission. We have very robust solar shielding in the form of the EOS, as Rob mentioned earlier, which helps increase the safety of our crew throughout the entire duration of the mission. All that is wrapped up in a very feasible mission cost, and I'd like to take a look at what the core of this mission is. It's to really prove the fact that we are a spacefaring nation, and we do want to bring back the age of space exploration. And not only will we be sending back pictures of humans at Mars, but we will also be sending pictures of humans at Venus. And with that, we'd like to thank you guys for listening to our presentation and invite the rest of our team to take any questions that you guys may have. Thank you. We know you guys got some, come on. Can we do audience questions? Is that okay?
Well, let me
Sure.
ask. You have a rather specific trajectory here. What's your windows on this? What's your margin for error?
So we have a 2-week launch window. I know typically JPL likes to have a 3-week, but beyond the 2-week, we start seeing an exponential increase in the launch V-infinity and the entry speed. So we are kind of constrained to 2-week. We have up to 6 days of boil off accounted for, and with the 30% mass margin on everything as an industry standard. That's basically our margins. Any specific margins you were looking for?
I wanted to know the launch window margins because you're banking a lot on this trajectory.
Yes.
Okay.
Yeah, I have a particular affection for thermal issues around Venus. You answered part of that, but as you're flying by Venus, it's hot itself. Have you calculated that?
No, we did not.
You know, I mean, I don't know. I mean, for lunar missions, for example, I almost lost a spacecraft to lunar orbit once because of not calculating.
That would definitely be
hot.
something we need to look into.
With the communications, obviously I saw you focusing on the laser because of a bunch of advantages, but comms are quite an important part of your mission safety and things like that. Have you looked at the issue of having backup systems and the weight and cost of having conventional systems as well?
So that's why we're bringing the 1 meter backup dish. That could be increased in size depending on whether it fits in the fairing with the rest of the vehicle. However, we wanted that high data rate for that HD video and that human interaction between mission on Earth and with the crew. And so the deep space optical communication we feel was a necessary primary communication system. Any other questions? We have one from the audience. That is true, and a very valid point. The question was, how did we balance the short time of flight with the fact that we're entering quickly? And so we felt that the EDL aspect was one of the large risk areas. However, we also get an additional 2 years of development time in order to prove out these technologies versus a 2021 trajectory. In addition, as was presented earlier with the 2-year free return trajectory, you also get high entry speeds every once in a while. So it's not an absurdly larger number than some of the other designs. It's something that we'll eventually have to deal with if we are a spacefaring nation and species. If we want to visit other places, eventually we will have to enter at fast speeds.
If I got this correctly, you're foreseeing the 2 first launches within 2 days.
Yes.
I mean, this is unheard of. Yeah. Why do you think this is important?
Because we wanted to reduce boil off. We are holding on to that Falcon Heavy second stage. We need that propellant in there. And so if we waited too much longer, we would risk not having enough fuel. In addition, to address that point, NASA has had 2 shuttles on 2 different launch pads ready to go in case the first one had issues with the crew in orbit. So it wasn't needed, but at least it has been demonstrated that we can have 2 separate vehicles ready to go around the same time period. And since one is going to be a NASA vehicle, the SLS, and the other one is SpaceX, which they'll have different ground system teams, so they won't be interfering with each other, hopefully. That's the idea.
Time for one more question. All right, thank you very much.
Thank you.